Awesome. So welcome. As I said, my name's Kat. I'm going to be taking you through organic chemistry today. If you have any questions, please let us know, or if you're going too fast or too slow, let us know as well. Or if you can't hear me at any stage because the mic's cut out, just let us know as well. So as we said, at the very bottom of your screen, this is where you have your picture, you have your mic, you have your ability to share your camera and your hands up. So what I'd like everyone to do right now is just raise your hand so we know that you know where to find that little icon. Okay, just waiting on a few more. So just raise your hand on the icon.
So the targets are here. There we go.
All right, beautiful. So everyone now lower your hands. Perfect. You need to know how to do both. It's faster for us all. And now here's the next part where you find your chat. So you come down to the very bottom where you've got this purple arrow here. Click on there and it opens up a little panel. It's your collaborate panel. Oops. And in there you have your everyone chat and things like that. So what I'd like everybody to do is just to type hi in the everyone chat just so we know that you know where to find it. Nicely done. Yeah, they're all over it. The last thing I wanted you to do is at the very bottom here, click on to your little human, so the little cutout, and a little box will pop up. And I want to click whether you're happy, sad, whether you're confused, whether you approve or disapprove. So just click something just so we know that you know where to find this for us. So this is a way that you guys can communicate with us if you're saying you're going too fast or too slow. Awesome work, guys. So this is more so for your teachers, but it is good for you guys to see as well. This here is all the dot points that we're hopefully touching or covering today. What is the purpose of today's session? So first thing, we want to be able to interpret your infrared, our proton NMR and our carbon-13 NMR spectrums. We want to be able to analyse and determine the chemical structure of an unknown sample or samples. And we want to be able to construct a calibration curve from the concentrations of, and then find an unknown concentration, which is pretty cool. So here's a bit of an overview for what we've done today. And you'll see here we had some pre-work for you to do. If you haven't done it, it's not the end of the world. It's just there to help you. You've got 5 questions that are past exam questions. And then today we're going to be going through the analysis of the infrared and NMR spectrums. And then we're going to be using our HPLC. The last thing is to follow up after this session. You've got 3 unknowns that your teachers can go through with you, and they'll be getting the PowerPoints as the solutions to go through. And there's a post-work quiz, which is 10 past exam papers, and then there's a post-prem survey, which we please ask that you do at the end, because then we have some idea if this program's helping you or if there's something cool we could do, things like that. So let's get started. Here is our case study that we'll be doing today. We have patient X who has been found unconscious and unresponsive on their bedroom floor. So their partners found them, called an ambulance, and when they got there, they found a black liquid beside them, which the ambulance officer was able to pour into another container. When they were taken to hospital, they were able to use this to help diagnose what was wrong with our particular patient. And when they actually spoke to the patient's partner, they said that they were experiencing things like anxiety, insomnia, so that's trouble sleeping, high blood pressure, rapid heart rate, and increased urination. While patient X was in hospital, they were able to collect 3 litres of urine in a 24-hour period. So your job today as our organic chemist is to analyse the unknown compounds in the urine and the black liquid. And this is where it all starts. So microanalysis, the first thing they found that both the compound in the urine and the black liquid was identical. So that's really good. You don't have to do 2 sets of spectras. They were able to find that the unknown compound had 49.18% carbon, 5.39% hydrogen, 28.65% nitrogen, and 16.68% oxygen. And this was done by mass percentage. They were able to determine the molar mass as 196 grams per mole. Now, this all comes from a particular machine which has been removed from the course for you guys this year. It's a mass spectra. We don't need to teach it this year, but it is good to understand where it's actually come from. So what we now need for you to do is to log into your Canvas, and when you have logged in, raise your hand. You are going to go to the microanalysis quiz and calculate your empirical and molecular formula. So when you're in your Canvas shell, raise your hand, just so we know, and if anyone's having problems getting on there, please let us know in the chat and we'll help you out. So raise your hand once you're into Canvas and start with the microanalysis quiz. If you've got any dramas, as I said, we'll be here waiting. We're going to give you about 10 minutes to answer this, and then you can come back and we'll help you out. So I'm going to mute, so you have to listen to me mumbling in the background. But once you have logged into Canvas, just raise your hand. When you get back, there'll be a poll waiting for you. Okay, guys, can we all jump back in to collaborate now? Answer the poll when you jump back in. If you haven't completed your calculations, that's okay. You'll have time to do this after this session as well. So jumping back in, answering the poll. How many are we waiting on?
About 9.
Okay, so waiting on 9 of you to answer.
A lot of people just came in.
Oh, wow, that was just like a whole heap of you then.
Just got 3 or 4.
Okay, 3. So, yeah, student teacher.
Waiting on 1 student, but it's double up, so just Michael and Leah's the only one we need an answer from.
If you're unsure, that's fine. Just have a guess.
You have a best guess.
Okay. Showing the responses now. So as you can see, most of you have picked the 3rd option, which is the correct option. So it is your C4H5N2O. So let's go through how we actually work this out. So for your empirical formula, this is the way I like to visualize it. It makes it easier for me to position everything. Basically what I do is I go through and I put into a table. So you put your carbon, your hydrogen, nitrogen, oxygen, put in your percentages, and because it's a percentage, when you times it by 100, that gives you your mass in grams. From there, you then use your periodic table, and you use for carbon 12.0, 1.0, 14.0, and 16.0. Then from there, we work out our mole, and as you can see, we've done for the rest of them. You choose your smallest mole, which in this case is our oxygen, divide it by that one to get your ratio, and as you can see here, it's pretty close, so you can actually round them. If they're really big differences, then you will need to times it by 2 or 3 to get a more whole number. So working it out, we have our carbon 4, hydrogen 5, nitrogen 2, and our oxygen. From here, we can then confer if our molecular formula is our empirical formula as well. So we first started off knowing that our molecular formula's molar mass is 196 grams per mole. So now we need to calculate our empirical formula's molecular formula. So you simply go 4 times your carbon, 5 times your hydrogen, 4 times your nitrogen, 1 times your oxygen. So you plug those numbers in and you end up with 97 grams per mole. So now we need to do our ratio. So 196 divided by our 97, and it comes out at about 2. So we need to times our empirical formula by 2, which then allows us to give our molecular formula of C8H10N4O2. So from here, we now start to look at our infrared. So in regards to our infrared, this basically gives us a bit of a snapshot as to what functional groups we have within our unknown compound. And at the top here, you've got your table. This table just comes out of your data booklet. And so this just gives you a bit of a snapshot of what we'll be looking for. This here is also on the Canvas shell for you. It's a really cool overview of all the different organic functional groups. There are more here than you require for as a VCE student, but it's really cool to actually see how they are positioned. So it's giving you more information. And here is another one from your compound of interest, so Compound Chem. They are a pretty cool website. And you can see here, it actually shows the stretches and it shows where there is twisting and things like that within your functional groups. So if you're unsure as to where things are sitting, it gives you a bit more of an understanding. So here is our unknowns spectra, and you'll see it's very noisy down here in the fingerprint region. So this is one of the problems when it comes to infrared. You can get quite a bit of noise with it. So what I want you to do now is go back into Canvas, and I'd like you to answer the questions for the infrared quiz. Once you've finished that, jump back in and there'll be a quiz waiting for you. Now, I'm not so evil. I'm not going to get you to answer every number what it means. All I want you to do is, with the 3 drop boxes, answer which particular functional group you think it is. So when you're done, guys, jump back in and there'll be a poll waiting for you. I'm going to give you about 5 minutes to do this in. All right, guys, so jumping back in to collaborate to answer the poll. Just waiting on a few more of you to answer. You must have all jumped back in the last 5 seconds. How many more we got to go, Alex?
We're just waiting on Bhubanesh, if I say his name right, and Wally, who's just answered. So we're just waiting on...
There we go, awesome. Showing you the response now. So most of you have smashed it out of the park, well done. So let's go through and have a look at the solutions. So here we've got our first one, and that is our carbon to hydrogen at 2,935 centimetres, and that's your alkanes, or it could be alkenes. Then we have our next one at 1,693, and that is a carbon to carbon double bond, so it's an alkene. And our last one's a really interesting one. It's 1,644, and that is a carbon double bonded to oxygen, but where it's sitting is looking like a amide, which therefore means that we're looking at where our nitrogens are sitting, which is really useful because we have a few of those in our compound. So now we're going to have a look at our NMRs. But before we continue, who can tell me what NMR stands for? Just type it in the chat or put on your microphone. Who can tell me what that NMR stands for? Here we go. Beautiful, well done. It is your nuclear magnetic resonance, well done. Okay, so the whole point of this allows us to determine our carbon environments. So basically one peak is representative of a carbon environment that we have. And your chemical shift lets you know what is bonded around it. The last part, there is no integration like you have for your proton NMR. So the height of it doesn't let us know that how many carbons are in that particular environment. But here's a really interesting bit of information for side information. If there is no hydrogens bonded to your carbon, you generally have a smaller peak. And just like before, this data here is just straight out of your table. This here's another image from your compound interest, so your compound chem, and it's showing you those particular functional groups where they sit with their chemical shift. And the last thing I need to point out is that we're using carbon-13, and there's only 1% of carbon-13 on our planet, so it's actually really hard, and this has only been used in probably the last 20 years, which is pretty amazing. So here is our unknown for our particular compound. The other thing I forgot to say is all our unknowns have all been recorded and given us information from our Hawthorn campus, which reminds me, I forgot to show the video. It's not popping up to remind me to play videos. Whoopsie. And here is our hydrogen, so our proton NMR. And this here, as you can see, just like our carbon, it shows us the proton environments. Here we have the number of peaks, but here this tells us our proton environments. We've got our chemical shift, which tells us what it's bonded to, and then you've got your integration, which is its height, so how many protons are in that particular environment. The last one, which is really interesting, is our splitting. So if you end up with a hydrogen that's got other protons sitting around it, it will then split. So if you have two that are its neighbour, so 2 plus 1 gives you 3, so you end up with a triplet. And here is our little graph here. Last thing I wanted to show you, this part is talking about the singlets, the doublets and triplets. So that's depending on how many neighbours it has that has protons bonded to it. And this here is its particular spectra. Now, before I continue, I'm just going to show you the really cool machines that this has come from. So I'm just going to show you the infrared, which I forgot to do, and then I'll show the other two. My apologies for getting what I'm doing. Okay, so here's our infrared. This is an FTIR, and it's just a benchtop little spectra. And the first thing you need to do is run a background check, so you're clearing any other things that are in there. You then take your sample. So this is for infrared, so I probably forgot to show this. You put 2 drops to the top there, and then you simply just run and you get your spectra. Pretty straightforward, really cool little machine. The next one I'm going to show you is our benchtop.
Just noting that's about 3 seconds behind what we're saying.
Cool. Yeah. So the next one is our carbon-13 NMR. The first thing you need to do with this particular one is called shimming, and this is basically resetting your magnetic fields. So it gets put into here, and then the holder from here then gets placed into the machine, and then you have to shim. So this is sort of like recalibrating everything for you before you run your sample. So you simply get into your system, click on shim, and then push start. And then once you've got a successful shim, you then can get your sample. And just like with the infrared, you get your tube and you put in a couple drops. From here, you put it in your holder, and then you place it into your NMR. You've got to make sure it's positioned in the right spot, because you don't actually want the magnetic field running through the wrong area. And then once you're ready, the really cool thing is with these spin solves, you can have a proton NMR or a carbon-13 NMR. So this particular one that they did the spectra for was a proton NMR. The last one I would love to have here. It is a really cool machine. It's only $500,000. I don't know why my bosses won't buy me one. I can beg, can't I? So this sample gets placed into the sample express at the top. It's a bit like a conveyor belt. So if you notice at the top here, there's a green light. You push your sample express to make it go. You then come over and say, yes, I'm ready for my sample to head in. And when we head back to the machine, so just like we did before, you have to do a calibration and everything. Notice here at the top, there is a red flashing light, and you'll see them slowly spinning. So once it's in the actual spot, it will go green again, and then you can load your sample. So if you guys were to have come with us on an amazing trip to Hawthorn, you would have gone and seen these machines. But sadly, because of COVID, we're not allowed to go to Hawthorn and do excursions and things like that. So from here, you go back to your computer, you select all your parameters that you need, and then you can run. So we were really lucky. Our proton NMR spectra was actually from that machine. So jumping back onto here, this is the spectrum that I was talking to you about before. Now what I need you to do is jump back into Canvas, and I'd like you to answer the quiz on the NMR. There's about 4 questions, and once you're done, jump back in and there'll be a poll waiting for you. I'm going to give you 5 minutes again. So see you guys in about 5 minutes to answer your poll. Okay guys, jumping back in to collaborate. So if you haven't answered our poll sitting there, please do so. If you're unsure, it's okay, just have a guess. Waiting on 3. Waiting on 2. Waiting on 1. Okay, well done. Showing the responses now. So most of you have done very well there. So of course the correct answer is the last one. So let's go through it now. So we're going to go through our carbon-13 NMR first. So as you can see here, we have 8 blue circles which are showing our 8 peaks. So we have 8 carbon elements. We also can see that there are some that are more de-shielded at the end here, which means they must have something like nitrogens or double bonded to your oxygens. So therefore it's giving us a bit of a hint with our structure. The next one is our proton NMR. And the first part you'll see that we have 4 proton environments shown here in orange. We also notice that there's no splitting. The other interesting part is we've got our de-shielding here. So we know that this particular proton has a lot of de-shielding going on, so it's had a chemical shift occur to it. The last thing, which is really important for us, especially when we're adding it all up, you'll notice that these first 3 peaks are higher than the other peak over here that's been de-shielded. And they're about 3 times the size, which is giving us a clue that these may be methyl groups. And if we were to add this up, 3 protons on each of those is 9. 1 over here, that gives us our 10. So we're heading in the right direction. So I'm now going to hand over to Janine to give you a bit of a help with your solution of what compound we're playing with. And just a bit of a heads up, you would never get this compound on your exam because it's a really mean one to do. So handing over to you, Janine, now.
Hi everyone, I'm Janine. As Kat has said, I'm going to take you through the next couple of slides. So we've gathered all of our information about this compound, and our aim is to try and work out what it is. And as Kat also just mentioned, this compound is more complex than what you would expect to get on one of your tests or exams. So what we've done, instead of asking you to fully work out what it is, you will have a question where you have 4 compounds to decide between which one it is. So first of all, if we put all of our information together and see what we do know about it, we have the molecular formula. So we know that it has 8 carbons, 10 hydrogens, 4 nitrogens, and 2 oxygens. And from our infrared spectrum, we know that it has a carbon-oxygen double bond in a position which implies that it is an amide. We know that there's there's a carbon-carbon double bond, and we have carbon-hydrogen bonds. From our NMR, we know, first of all, the carbon-13 NMR, we know that not only do we have 8 carbons, as the molecular formula tells us, but we actually have 8 carbon environments. And 4 of them are de-shielded, which would indicate maybe our carbons bonded to oxygen or nitrogen in this particular example. Then coming down to our hydrogen NMR, we know that we have 4 proton environments, and look at the heights of the peaks. We know that 3 of the peaks are 3 times as high as one of the other peaks, and that one other peak, so that would indicate is a single proton and it's de-shielded. And then the other 3 that are 3 times as high would indicate to us that we have 3 methyl groups. The other interesting thing is we have no splitting in our hydrogen NMR spectra. So that tells us that our hydrogens are not in neighbouring environments. So we've got a fair bit of information there that we can put together, and then if we go to our next slide, we can have a look. You've been given 4 different compounds here to determine what it is. It's one of these 4. So we're not asking you to entirely work out what it is, but we can partly use a process of elimination. Now, if we have the names of the compounds on here. The first compound is adenosine. The next one is caffeine. Then we have octanoic acid, and the final one, which is quite difficult to say, oxalic acid diimidazolide. So if you go to your Canvas now, there's a question for you to have a go at working out which one of these.
No, sorry, there's a poll question up for them to answer.
Oh, sorry. Okay, so this is the question. You don't need to go to Canvas. It's already here. And there's a poll. So have a go. See which of these you believe it is, and I'll give you some time to work that out, and then put your answer in the poll and we'll have a talk about it. All right, so I think we'll move on. Looking at the poll, lots of answers, lots of people with the correct answer, which is caffeine. So well done. So let's just have a look at why it would be caffeine. So one of those things we can do, which is look at work out the molecular formula of each of these substances. Yeah, okay, so we have, if you look at compound C, it doesn't contain any nitrogen. So octanoic acid, we can eliminate that straight away because we know that our compound has 4 nitrogens. So we can eliminate that one. Then if we have a look at adenosine, we can see that it's actually got 5 nitrogens and our compound only has 4. So again, we can eliminate that very quickly. Then looking at our last 2 compounds that are left, caffeine and oxalic acid diimidazolide, if we could look at their molecular formulas to eliminate, but we also need to bear in mind that the purpose of this activity is to practice looking at our spectra and working out what our compound is from that. So if we have a look at oxalic acid, diimidazolide, sorry, first of all, we can see it has got 8 carbons, but if we look at the shape of it, it's a symmetrical molecule. There is as if there's a mirror line cutting through here, and when molecules have mirroring in them, what that does is reduces, in this case, the number of carbon environments. So you can see, for instance, the carbons bonded to each double bonded onto the oxygens and then onto the nitrogen, making our amide groups. For example, they are both in exactly the same carbon environment. So just by looking at that, we can see that we already will not have 8 carbon environments in this molecule. And as you work your way through, there's a number of other carbons that are in exactly the same environment. So due to that, we can eliminate example D. Also, if you look at the number of hydrogens, this compound only has 6 hydrogens and our unknown has 10. So looking at caffeine, we can look at the molecular formula and straight away say that it is our sample based on it being one of these 4. However, it's good, I think, to also look more closely at the structure of it to see that it does fit with what our spectra are telling us. So we can see we have our amides, amide groups. We have carbon double bonds. We have carbon-hydrogen bonds. We have one hydrogen. If we look, considering the well, maybe first of all look at the carbon NMR. If you look at each of these carbons, they are actually in a different environment. We have 8 carbon environments on this molecule when you look at what they're bonded to and then what those atoms are bonded to. And with the hydrogen NMR, we have 4 proton environments. Each of these methyl groups is in a different environment. So we've got our 3 methyl groups as we predicted, and then we have 1 single proton that's bonded between the 2 onto the carbon that's between the 2 nitrogen groups. So our compound is caffeine, and it fits with what we have observed on our spectra. So now I'm going to hand back over to Kat, who's going to talk to you some more about caffeine.
Thank you so much for that, Janine.
Thank you.
Okay, so now guys, we've worked out that it's caffeine, which is really cool, but we need to know why caffeine is so bad or so good for us. So we now need to go into working out why it's so important we know how much we are consuming and where caffeine is actually found. So as we've been discussing, you can see that we've got our different functional groups. We've got our amine at the top and our amides at the bottom. And why is this so important? It's because when we look at our HPLC, we need to know whether we're dealing with a non-polar or polar compound. So in our case, because of those 2 functional groups, or 3 technically, that are sitting there, it gives us a non-polar compound. So when we go to put it into our HPLC, we now know that we need to have a polar mobile phase moving through. So here is just a bit of a snapshot of a HPLC. So at the start here, you have your solvent, so your mobile phase. In our case, we are using methanol. And it needs to be degassed because you don't need bubbles going through your column because it actually breaks your column, and columns start at about $1,000. So we don't want to break those. So moving through, you go to your pump, and that's what makes this special machine do something. So can anyone tell me what they think this pump does? Your clue is HPLC. What does that stand for, HPLC? Can someone jump into the comments and tell me what HPLC stands for? And give you a bit of a hint, there's two that you can call it. So HPLC, what does it stand for? Yes, the pump increases the pressure. Awesome. So what does HPLC stand for then?
So Spencer said high performance liquid chromatography.
So we've got high performance, and the other one is high. You've just told me what the pump does. Well done, guys. So if we've got high performance, and what's our other one?
High pressure.
Well done. Excellent work. So high pressure liquid chromatography. So that pump there is what is making this a high performance or high pressure. So then from here, we move up to our porthole, which is our injection site, where you inject your sample. Then from here, with the mobile phase being at high pressure, it goes through the column, and in there you've got your little beads. So as your compound and your mobile phase are moving through, it is then slowly being separated in there. Once it's been separated, you head into your detector, and this is where the detector sees where the separations have occurred. And on your computer, you get your lovely calibration, or sorry, your retention times and your area under, so you get your nice little peak. So in regards to caffeine, we need to have our UV detector sitting at 260 to 270 nanometers. So this helps us to get the correct absorbance when we're running it through the HPLC. So now we're going to jump into the lab, and I'm going to stop sharing my screen. Okay, so we're going to jump into our lab now, and we're going to talk you through how we actually make our standards, because we need to make our standards before we can work out the unknown concentration of our caffeine. So the first thing, I remembered it today, we need to put on our safety glasses. When you guys make up your stock solutions, you generally use one of these, a volumetric flask. But because we are using such small volumes, you need to use one of these little containers. And we're going to be using a micro pipette. Can you raise your hand if you've used a micro pipette before? Oh, good work, Leanne. Awesome, we've got a few of you that have used one before. That's okay. It's very rare. Funny, as a chemist, you don't generally use this as more of a biologist, but if you're using really small amounts, you will need to use your micro pipettes. So the first one we're going to be making, we're actually going to be using this big guy here, and I'm going to show you how to use it first. So at the top here, you've got a button, and you need to find two different stops. So you've got your first stop here, and that is drawing out all the air out of the barrel. Your second stop is all the way down to the bottom, and that is once you've got your liquid taken up, you can then pump it out into your container. So the first thing I need to do is to grab a tip, and because we're using 1,000 microliters, we actually need a really big tip, and we need to set how much we need. So simply by popping this one up, you simply turn that little knob at the top, and then you can set it to your amount. So you click it back in. So what we're going to do now is get our distilled water first, and then from there we are going to, and I've put my distilled water over here before. So we're going to get our distilled water. Okay. The cheap's way of getting distilled water out. So you're going to find that first stop. go into your liquid, draw it up, and that is 1,000 microlitres in there. From here, I have my labelled container. I'm then going to pipette that into there. And then we're going to eject my little tip there. So that's my first one done. That is my blank. It's just distilled water. Then my next one, I'm going to be making my next standard, which is 3.75 milligrams per litre. And I'm going to be using this little micro pipette here. So just like the other one, we need to set it to our amount. Once we're set, we then grab our tip. So there's our tip all ready to go. And I'm going to be kneading our stock solution to make our So we've got our stock solution there of our caffeine. We're using 150 milligrams per litre. Now we're going to be getting 3.7 microlitres. It is so tiny, it's pretty much a little, so we put that in here. So when we come in, you'll see that tiny little dot there on the side. You able to get that, ET?
Not possible.
That tiny little dot is your 3.75 microlitres. So now I'm going to add that up so it equals our 1,000. So we're going to get a new tip on for our distilled water, and we're going to be putting in our 975. So pump that in. Now, if you guys were here with us, you would be creating all our standards. And then we go and put them into our HPLC. So a bit like a cook show, here's one we prepared earlier. We have them all sitting here, already all our standards ready to go. We also have our urine sample from our patient and the black liquid. So we're going to head over to our HPLC. So bear with us a moment as we move around. You okay, Alex?
Yeah, coming over.
So the first thing we're going to do is show you the machine. It's just warming up at the moment, so that's the pump you can hear. So at the very top here, you're right, Alex? What's wrong? The whole time? Okay, you all right, guys? We can make the calibrations again if they need. Where did they lose us?
I'm not sure they ever had you.
Okay, do they want us to show this again?
You got to ask.
So guys, do you need us to show again?
Okay, we saw the whole thing. Yep, they have.
Cool, all right, just wanted to make sure because we got lost for a little bit. Okay, so over here, we've got our HPLC. Can everyone see us? Awesome. So at the top here, we have our mobile phase. This is our methanol. It goes through down into our machine, down to the bottom, and this is where our pump is. Now at our pump, it splits into two, and this is to help with it degassing as well. From there, it comes around to where our injection port is, and this is where you inject your sample. It then comes up the back through the column, and then up the top here, comes around, and then you've got your UV detector sitting there. From there, it goes to the computer to give us our readout, but the waste has two spots that it comes out. The first one is your injection port here, so anything that's a waste sits here. The other one is that it goes all the way down the back and comes down to our waste port down here. Thank you. So what we're going to do is set this all up, and we'll get our first little sample here. That's in the wrong spot. Starts up. All right, so we've got our sample here. We have our blunt syringe, and we're just going to get a little bit of an amount out. All got it?
Yep.
Okay. Alrighty. I need another sample. There's hardly anything in there. Okay, so we put it into here. We'll see if this sample runs. If we need another sample, we can get some more. We eject it. Take a close look at this waste point here. Yep, we're all good. And see those little drops popping out? That's the excess. We then simply eject it in, and then coming over here, you'll start to see our baseline starting to occur. Do you want to jump in to fix it if it needs it? Just change it. So you need to go the other way. So you start to see that our pump is on, the ejection has happened, and we've got our detector on. So you can see our baseline is starting to try and correct itself. So sometimes your baselines can be a bit sketchy. So just come over here for a second and we'll show you what we mean by high pressure. So Alex is just going to point down to the bottom. And you can see it's running at 1,725 PSI. Okay, hang on. So change the zoom. Our HPLC has been a bit of an evil one today. So we'll just jump back over. You can see the peak coming through. It means that we've got something else in the background as well. So we're going to head back over to we'll stop this sample running because it's not playing nice games today. This is why you do previous ones beforehand. So we're going to jump back over to our device over here. And I'm going to show you a previously prepared one. So just jump into the matrix for a second. Okay, so here's one of our previous ones that has worked beautifully. So you see for your 0, you don't get anything. Your 3.7, you see that there's a little peak. 7.5, you see a bigger peak occurring. 11.25, you see it's a bit higher again. We've got 15. And then our last standard, which is at 18.75. And then these are all our standards together at once. And now we're going to show our unknowns. Now, as you saw, it took quite a while just to get that one little peak for us, and HPLCs can be a bit annoying at times. So there's your black liquid. If you are in here doing this with us, it takes 5 minutes per standard to run. So here's all of them running together at one time. So giving you a bit of a hint at concentrations there. So I'm going to stop sharing that one. And we're going to jump back into our PowerPoint. Just go time again, it's misbehaving. Okay, all back with me, beautiful. Now the other thing I wanted to say, on your canvas, there is a video about caffeine there. It's a really cool TED talk, and it goes into a bit of information about how much caffeine you should have daily and what caffeine is actually found in. But let's get back to what we need to do. So with your calibration curve that you need to create, I've got to ask you guys at the start, does everyone have a piece of paper, a pen, a ruler or graph paper to draw out a calibration curve? So raise your hand if you have graph paper or a ruler to draw your own calibration curve. Awesome, looks like you guys are pretty much all over it. Beautiful, your teacher's got that message. So what I want you to do is the first thing is to draw out your calibration curve with the information. So you've got your standards, and then you've got your peak transition, so your attention times, and then you've got your area under the graph. Then from there, I want you to get the two unknowns. So I want you to find out the concentration of the black liquid and the concentration of your urine sample. So you're going to have, I'm going to give you 10 minutes to do this in, and there'll be a poll question waiting for you when you head back. So you need to draw out your calibration curve and then work out the unknown concentrations of the black liquid and for your urine sample. Now, as I said, I'm a bit evil. I'm making you draw this by hand, and then you just need to take a picture of it and put it up as an image. So I'm going to give you 10 minutes. Have a go, guys. And when you get back, there'll be a poll question waiting for you. Okay, guys, everyone jumping back in because we're looking at the time and we're running out of time very fast. So jumping back in to collaborate. If you're unsure of your answer, that's okay. Have a guess. How many are we waiting on, Alex? 3 more to go, 2 more to go. Have a guess if you're unsure. One more to go. Okay, so you see that we got 2 answers here that are very similar, and you can see that there have been, you guys have picked those 2. Can someone tell me why you may end up with a different answer to the correct answer, which of course is the 3rd option? Why would you end up with a different answer when I gave you all the same information at the start to make your calibration curve? So just write a little text or let us know what you think. Why would we end up with a different answer? So remember, you all had the same information at the beginning, but you've ended up with different answers. What did I ask you to create? That's your clue. No one can tell me what I asked you to draw for me. Drew, that's terrible English. What did I ask for you to draw for me?
Very quiet group today. Some people say calibration curve, some people didn't sketch it, they did some maths.
Yep. So calibration curve, you can do this by maths. The easiest way is the calibration curve. So if you all have the same information, would your calibration curve be the same?
Shakira said no.
Why not? You got the same information. Why is your calibration curve different?
Says I don't know.
Don't know, that's all right. So it's because of human error. So it's all to do with how we actually plot our graph and things like that. Now, if this was a 4-point question in an exam, so your first point would be, or 2 points would be to draw the graph. The second one would be to work out the concentrations. Now, because you're using your graph to get your answer, if you get the incorrect answer for the actual amounts, it's because it's your graph. Now, you will not lose the marks as long as you're using the same information. That's why you need to show you're working out. So well done, guys. The correct answer was 43.11 milligrams. So you would have got a reading of about 14.37 milligrams per litre. And then, of course, the trick, you had to times it by 3 because that's how many litres were collected in the 24-hour period. Now, if you haven't had a chance to do any of the quizzes or anything, you can jump back in and do them later. So you've got this open to you all the time. You can go back and do your pre-work if you've missed any of it or want to recap anything. After this, we have some post-work questions for you. You've got 10 exam questions to practice, and you can come back and keep practicing them. The other thing is you have 3 unknowns to go through and work out what they are, and your teachers will be getting the answers to those. The last thing is please do the survey at the end because that helps us as teachers become better teachers. And lastly, good luck your exams. Thank you so much for coming today and listening to me ramble. Etienne, did you have the HPL image up still or no? So if you'd like, I'm going to stop sharing, and we actually got a better image than we did before because we actually were too close in. So this is the joys of technology. So Etienne's just logging in. And we'll just get the image up. Has it gone to sleep and run away? Oh no, that's okay. Our baseline's a bit off today. It's been a bit tricky.
That's right, we'll call it.
All right, guys. So thank you so much. The other thing I wanted to say is that, and our camera is on. Yep. The other thing I wanted to say is that your teacher's been given information about an app called Chemical Detectives. And Chemical Detectives is pretty cool because it allows you, oh, you got it? Well, it allows you to analyse one way or another. So you can start with a compound that you know and go, okay, I can see this is why we have the spectras like this. Or you have it flipping the other way where you can actually work out from the spectras what it is. So it's a really cool app. You can put it on your phone, an iPad, a tablet. I don't believe they have a website. Before we go, we do have the image of CT. So we're just going to take you over to show you it now. So have a good look. You can see that we've got our nice little peak there. It's a bit of a shaky peak, which means it's not very happy, but you can see you've got your baseline running along here and then your peak jumping up. So it's not very clean today. I think the wind's making everything upset at the moment. So thank you very much, guys. If you have any questions, please ask. Otherwise, I'm going to hand over to your teachers now and they can let you know what the next bit of instructions is. So thank you very much, and I'll hand you back to your teachers now.